right, it's 11:15. We'll get started. So any questions on the homework or any things people want to talk about in relation to the homework that is due tonight? Yes.
1.3 was kind of throwing me for a loop.
Great. 1.3. We will talk about 1.3 in detail today. It's in the notes. I will show you how to do 1.3 before we leave. Yeah. Other questions? Yes. Oh, what does it mean? What do the numbers mean? So you could talk about, you know, is it closer to 10,000? Is it closer to 100,000? You know, sort of, is it an easy way to take an average? So just comment on sort of what the number, what the answer is in relation to the other molecules. And I'll tell you, especially for 1.3, all of your answers for MN and MW should be between 100,000 and 10,000. So that's checking the reasonableness of your answer. If you get 1,000 for an MN or an MW, you're wrong. So basically the bounds of the answers are going to be between the molecular weights of the distribution. That should be obvious, but just as a check to make sure your answer is reasonable, all the answers are going to be between 10,000 and 100,000. And don't forget the units. So if it's degree of polymerization, what is the unit for degree of polymerization? N or X, what's that unit? Unitless. You could say that there's no units, but I prefer, as scientists and engineers, we say it's a unitless number. Or it'll be 360 repeat units. So repeat unit is really the unit, but you know. What is the units for MN and MW? Grams per mole. Put that down next to the number. On Canvas, there's no guarantee that I might have 40,000 with no unit, and then I might have 40,000 grams per mole with the units. You need to make sure to pick the one with the unit. So the number is half the answer, and the units are fully half the answer. If you can't figure out how to get the units right, you know, make sure you pay attention to that. Yes.
For 2.1, what observations specifically are we supposed to look for, like the weighting and net, or?
I will talk about 2.1 in class 2. Yeah. We're like half a lecture behind, so that's why we have a few extra questions, but I wanted to make sure to get you the homework so you're thinking about it, thinking ahead of me, and then we'll clean things up today. But I guarantee you, I looked at the homework this morning and made sure that the slides that we're going to cover today will cover those problems. Yeah, I'm not going to hang you out to dry most of the time. Questions? Anything else? All right, don't email me after 6 p.m. tonight or 7 p.m. The chances of you getting help after that late time are very low, unless you know, I'm working on my YouTube page or something like that. But anyway, get help soon rather than later. All right. So the reason why we care about this whole molecular weight business is that we're really interested in the size of a polymer chain. So we can figure out the dimensions, right? We can look up the dimensions of a carbon-hydrogen bond. Approximately how long is a carbon-hydrogen bond? Anyone know? Is it nanometers? Is it microns? Is it angstroms? What's the order of magnitude? Angstroms. And angstroms is 10 times smaller than a nanometer. So an angstrom is 10 to the minus 10 meters. It's really small. But how long is a polymer chain? Or how long can it be? Very, very long. That's right, especially for a molecule. Because what can N be? What are some reasonable values of N for polymers? 800, 5,000, 100,000. And so if you multiply, what's this structure called right here? What do we call that in polymers? Repeat unit, right? This is ethylene repeat unit or polyethylene repeat unit. And so the grams per mole or the molecular weight of the repeat unit is usually pretty small, like any sort of organic molecule, 50, 100, 18, 150, 300 sometimes. But as we start to multiply that by the degree of polymerization, we get huge molecular weights. And so what happens is that polymers are not a big long line as we usually draw them on paper. They coil up, they do all sorts of things, like this is aquaporin, which is a biological polymer or a protein. And so when they coil up, now they make big structures that you can see. So this scale bar here in this TEM, which is transmission electron microscopy, so it's not like a regular light microscope, but it's using electrons to give you a visual picture or image of the structure. How big is 50 nanometers compared to a carbon hydrogen bond that's 1 angstrom? How many more times is it? 500, right? So it's 50 nanometers. So it's 500 angstroms. So it's huge. These are big molecules. You can see them with electron microscopy. The smallest things that you can see in electron microscopy is like an atom. You've seen some pictures of atoms. So you can see an angstrom or an angstrom and a half or so, but these are gigantic molecules. And we can't always take a picture of a molecule of polyethylene, but we can get an idea of its size from its molecular weight. So that's why we care so much about molecular weight. Another really big polymer is DNA. And so this again is 50 nanometers, and this is a transmission electron microscope image. And so these are big polymers. You can start to visualize them. All right. Now, we have talked about 2 different types of polymers. If you remember our discussion of addition and condensation. So in this case, chain polymerization is addition. And then step polymerization, its other name is condensation. So as we go forward, we're going to talk mostly about molecular weight today and how to do all the math around molecular weight. But as we go forward, make sure that you're able to connect what we talked about with chain polymerization and addition, which are monomers that look like this, right? Versus step polymerization or condensation. What do the monomers look like in step polymerization or condensation? Yes. They're a little bit bigger. And what's the key feature of those monomers? Yeah. They have functional groups that make other functional groups, right? And so we'll generally write that A plus B. So we have a diamine and a diacid, or we have a dicarboxylic acid and we have a diol. Remember, diol means 2 alcohols. And so what's a common polymer that we make by step polymerization or condensation polymerization? Yes.
Nylon.
Nylon, good one. Let's call it polyamide. Because when we say nylon, that doesn't tell you what the functional group is. And so if you're really getting into it, nylon is polyamide, but I'll try and use polyamide in this class to remind you, look for the amides. What's another step or condensation polymer that we've talked about already? Some of you are drinking out of it right now. Yeah. Polyester or PET. Polyester. Great. And so we know how to make amides. We know how to make esters based on what we've done with organic chemistry. What are some common chain or addition polymers that we've discussed already in class? What's the most common polymer on the face of the earth other than DNA and cellulose? Yes. Polystyrene. That's not the most common. Polyethylene is the most common. Polyethylene, polystyrene, PVC, polyvinyl chloride. These polymers Yes.
So for the step polymerization, do all those like O's mean that it's the same monomer over and over again?
Yeah, it's a little, well, it means it's the same repeat unit over and over again. This is not the greatest drawing. We'll have some better drawings, but it sort of contrasts it with chain polymerization. And so I prefer AABB, and then the repeat unit you could draw around once you connect an A monomer and a B monomer together, then you get the repeat unit. So this diagram is not perfect in relation to the exact chemistry. Yeah, good question. And so what I was going to say is that these 5 polymers we've talked about, we've discussed, we've looked at their chemical structures. You should write them down and have them on a sheet next to you and learn them. In the exams, you will have a note sheet, and I will describe what that is. And so you want to start to build up some of your chemical structure drawing. If I ask you, please write down a addition polymer. Boom, you've got it right in your head. Oh, I know exactly how to draw polystyrene. I don't even have to think about it. Or please write down a polyamide structure. Okay, I know what polyamides are. I just have to remember to count the carbons and get everything in the right places, but I can write that down. And so this is where your own practice really becomes important. I'm mostly going to ask you about polymers that we've discussed in depth in class. And if you have to look something up, like methyl methacrylate or something like that, like on the homework, ethylene glycol dimethacrylate, I'll give you a table and I'll show you what the structure is. I don't expect you to memorize some of the more complicated stuff, but these are pretty simple polymers. These are bread and butter. And so you should have these right in your back pocket, ready to go when I ask you about a polymer. Any questions? Okay, and this is coming up to what you're going to need on the homework. And so we're going to talk about this in depth when we talk about how polymers are put together. But you can remember chain growth in terms of a chain reaction. And is a chain reaction fast or slow? Sort of in your heads. Fast, yeah. Boom, chain reaction explosion. It's a big deal, which means you get polymer quickly. So in order to make a polymer, you start with a big jar of monomers, and then you start the polymerization, or you initiate the polymerization either through an initiator or through heat. We'll talk about that. But as soon as you start the polymer in a chain or addition polymerization, remember there's 2 names for it, boom, you get polymer very quickly. In a step growth polymerization, this proceeds step by step. And when you think about just taking, 1 foot in front of the other, step by step, I get polymer, or I get to where I'm going pretty slowly. And so you can think of taking small steps at a time. We get polymer slowly. That's how I remember how polymers form, what grows quickly, what grows slowly. And so the technical way that this is depicted, and I'll draw the graph. So we've described it in words. You sort of have a picture in your heads. Okay, chain reaction is fast. And so let's make a plot. So this is molecular weight. Because if I'm making polymer, that means the molecular weight is probably going to be high or low if I have polymer. High. Molecular weight of polymers are high. And so I'm going to get molecular weight as a function of extent of reaction of monomers, or conversion. So extent of reaction of monomers of 0 means I have all monomer. Extent of reaction of monomers of 1, this is all polymer. And we'll talk a lot about that in the future, but just keep this plot in your head, all monomer. And of course, between 0 and 1, I've got a mixture of polymers and monomers because I'm still growing polymers in there. But for chain or addition polymerization, if I get polymer quickly in that chain reaction, boom, molecular weight goes right up and then levels off, and we'll talk about the leveling off later. But we get fast conversion of monomer to polymer. And if we're slowly taking step by step, very slowly, eventually I'll get polymer. This is 4-step polymerization. Slow molecular weight buildup. We'll go into the scientific reasons of why that is, but this will help you answer the homework, which polymerization mechanism or which type of polymerization reaction or which type of polymers grow quickly in a chain reaction and which type of polymers grow very slowly, step by step. I think that gives you enough information. And remember, the sections in the book that are for this week have this information in it. We just hadn't covered it in class yet. So if you wanted to look ahead, you can look in the syllabus and say, okay, this is in section 3.2 in the book. I'll go take a look at it. Don't forget about the book. Questions? Yes. For the step. No, the step polymerization goes at it's an asymptote at 1, and we'll talk about the math why. It doesn't go up and then level out. It looks just like this. It actually goes to infinity at 1, and we'll cover the mathematical reason why. Of course, we never have a molecular weight of a polymer that's infinity, but that's the limit of the equation. I know that you want to talk about limits and you want to talk about theoretically, this is what happens, but that's how the math works out. And I'll show you the equations you'll need next week. Yes?
So in the homework, if you just say condensation, polymerization, that's synonymous with step.
Yeah.
So I don't have to say step and condensation.
No, you can use condensation or you can use step. I know they mean the same thing. Yeah. You want to practice. Now the homework is your practice. So writing those two words together in step growth or condensation polymerization, the molecular weight buildup is slow. That's good because then you practice that answer. And because on the exam, I might ask you about step polymerization. I might ask you about condensation polymerization. You need to know that they're the same. Yeah. So don't forget to make a complete answer because it's good practice. Yeah. Other questions or anything that people want to chat about on this? Yes.
Why is that polymerization, although it is slower than chain polymerization?
Yeah, this is a really good question. Why do you need two different polymerization mechanisms? Why would you use the slow one? And the answer is that you can't make PET, you can't make nylons, you can't make a lot of different polymers with only chain polymerization. You can only make it with step growth polymerization. And so these different polymers have different properties, and so you need both. That's a good question. Any other questions? Yes.
So is it possible for a polymerization reaction to have both qualities, like both addition and condensation?
Not in this class. If there is mixed polymerization, it will be obvious. You'll be able to see it because what is the signature of addition polymerization? No byproducts. And what if you just look at a monomer, how do you know it's going to be addition? Carbon double bond, carbon double bond, nothing else, no oxygens, nothing like that. And so sometimes you can do a condensation polymerization with monomers that have double bonds. and then do an addition polymerization after that, but that's in your advanced synthesis class. We're not going to do that here. It should be from the type of monomer, completely obvious about what type of polymerization you're going to do, step growth or chain growth. And the key is this monomer right here, because these are really easy to recognize, right? The condensation monomers are always not that easy to recognize because you have to remember, okay, carboxylic acid and amine, or carboxylic acid and alcohol. You know, you need to figure that out. It's really easy to see double bonds. And you never open a double bond in step polymerization. So all the step polymerization monomers that we'll talk about don't have obvious carbon-carbon double bonds in them that you have to figure out what to do with. It's all going to be functional groups in organic chemistry. Other questions? All right, you should be set with that. And so now let's go to molecular weight. You should know how to do this. I think we've talked about this slide already. There's some nomenclature in here that you just want to be up on. M bar 0 is what? Go ahead. Molar mass of the repeat unit, right? And so if we want to describe the molecular weight of the chain, or the molar mass of the polymer chain, intuitively, you know that you just multiply the molecular weight of the repeat unit times the degree of polymerization, but this gives you the equation that you can go backwards and forwards. And so sometimes you'll know the molecular weight of the chain and the repeat unit molar mass, and I'll ask you what the degree of polymerization is. And remember, X, N, and X are the same. We've talked about that before. All right, let us get to, and you know how to do this. And so remember, the key for the copolymer equation, or M0 of a copolymer, is that this is a weighted average based on mole fraction. So you need to know what X, Y, and Z are in moles to get your M bar 0 of the copolymer. And so I think you have a homework question asking you what the degree of polymerization is of a copolymer. And so a really good way to solve that is to figure out M0 copolymer. And then you get the degree of polymerization of the whole thing, which is the sum of X, Y, and Z, or X and Y in the case of the homework. So you can solve it exactly the same way you would solve it for a homopolymer. You just need to figure out M0, M bar 0 copolymer. Is that clear? Yes.
How do you get the fractions in front of the weights again? 1.2.
Yeah, so you have to be given that. So in this case, I think we say, well, here, do I tell you what it is? Well, I would tell you what it is, but in this case, X equals 0.2, Y equals 0.3, and what do I have left? Z equals 0.5. What's the magic thing about mole fractions? What do they all add to? 1. Same with mass fractions, and so you know you can't be wrong if you can add them up to 1, right? Yeah, this must be a orphaned slide, but I would have to tell you that, or I would have to tell you the weight fraction, and you'd have to calculate the mole fraction like you have to do in the homework too. Yes.
So on the homework 1.2 plus 1.2 and ask for the number of times on the component. That's not separate. It's just the whole thing.
It's just the whole thing. That's right. It's the lumped number. So you get one number for the number average degree. All right, and that number should be about. So what's a reasonable number for X or N? I mean, I guess we talked about it on the very first slide, right? How do you know that you're actually calculating reasonable numbers? It's going to be like hundreds, maybe thousands. You know, if it's a really short oligomer, it might be 15, but it's not going to be 0.6. You know, it's probably not going to be 10 to the 10, right? And so as you start to get familiar with polymers, you need to have some sense of what's a reasonable number and what's not a reasonable number. And that will help you ward off calculation errors, right? You get something in the wrong place, calculator blows up, you don't know what's going on. And so make sure when you're calculating things, you're like, is that reasonable? Can a polymer have a X bar N copolymer degree of polymerization of 1300? Okay, I think that's a reasonable number, right? I can move on. And you can, if you get a fraction or something, if you're using decimal places and you get like 876.4, just round down, round up, to the nearest monomer unit. Degree of polymerization really has to be a whole number, but it sometimes comes out a little funky. That's life. Any other questions? All right. So we're not only using this to make sure you have all the knowledge that you need for the homework. Hopefully you're going to remember some of this stuff and use it. And so we've been talking about single molar masses, but as we left off on last time, molar mass is a distribution, which means you have molar mass down here, you have weight fraction in this case, and so you have a bunch of different molecules of different molecular weight that make up this distribution. And there's two types of averages that we're going to use to describe this distribution. We're going to use MN, which is called the first moment of the distribution. And I'll show you why it's called the first moment in a second. And then we're going to use MW, which is the second moment of the distribution. And there's some rules about MN and MW. And so MN or MW is either greater than or equal to MN. And then we have a quantity called dispersity, and I have a slide on that, but I just want to introduce it right now, equals MW divided by MN. What are the units of MW? Grams per mole. Units of MN are grams per mole. So what are the units of dispersity? Unitless. Perfect. And what is the range of values that you can get for dispersity? What are the limits? Yes. So mathematically, let's not worry about practically, but mathematically, so you can get 1, right? Or if MW can be greater or equal to MN, can you go above 1? Yeah. Can you go below 1? No. So dispersity is always 1 or greater. It can be 7, it can be 10, it can be 15. That happens. It will generally be 1, 1.2, 1.5. It'll be 2 theoretically for some polymers. We'll talk about that. But having the equation and knowing the rules about MW and MN will get you in the ballpark. Yes. Not always. For a monodisperse sample, which means every single chain has exactly the same length, MN equals MW, and dispersity is 1.0 by definition. Now that's hard to achieve in real life, but there have been polymers where the dispersity is like 1.02 or something like that. You can make that sample. People work on that as a research project, but for monodispersed sample is defined as dispersity equals 1. Yes. So dispersity characterizes the breadth of this distribution. I can't really draw it on this plot. It's not related to the shape of the plot, but it characterizes how wide that distribution is. Yeah. So it basically tells you the distance between MN and MW. And so that's a description of the breadth of the distribution. Just like if you do signal processing or something, like the full width at half maximum, it's not that, but it's like that. How wide is this peak? Or how many different types of molecular weights are in the distribution? Good. All right, now here comes the math, and you'll need this for the homework. So the number average molar mass is easy. You just take mole fraction times the molar mass of the molecule, and you can get the Mn. So remember, Mn is always the easy one. That's why it's called the first moment. But it's based on moles. X, I, and that's capital XI, mole fraction. If you try and do this with weight fraction, you're going to be wrong. There's a different equation for weight fraction. And MW, of course, has a different equation. But remember, Mn is based on the number of moles. And so this summation, you should be familiar with this. So you can have capital XI, which is the mole fraction. But of course, this is the same thing because you just take the moles of whatever you're talking about divided by total moles. So make sure you're okay with summation notation and how to get mole fractions from moles and things like that. And we have a nice example. So you're given a sample like this, 1 mole of 10 kilograms per mole chains. That means the chain, there's a mole of chains that all have an Mn of 10,000 grams per mole. If I don't say Mn or Mw, if it's just capital M, it means Mn. 2 moles of 12 kilogram per mole, make sure that's kilogram per mole, so 12,000 grams per mole, then 1 mole of this. And so now we can just sum it up, right? Mole fraction times its molecular weight plus mole fraction times its molecular weight, mole fraction times its molecular weight. And so these equations, of course, are exactly the same because the denominator's the same in all of those terms. And so you get 12 kilograms per mole is the Mn. Now, don't get confused that the Mn is 12 kilograms per mole. And it just so happens that our center chains are 12 kilograms per mole. That's just how the math came out. If we had, say, 6 moles of Mn 14 kilogram per mole chains, we have a higher number, right? Now we wouldn't have 12. So don't just think that the center population is going to give you the Mn. It depends on the weighted average of the mole fractions. Is anyone confused at this point? Okay, always remember that Mn is the easy one. You don't have to square anything, but it's based on moles. Yes?
So do we use either equation to solve that? Looks like.
Yeah, they're mathematically identical. Yeah. But it's based on moles. So if I give you weights, you have to change it, right? All right, any other questions? Yes?
So then going back to the homework problem concept, is like equal enough and no matter what.
Well, I think it asks you equal weights, right? Or does it say equal moles? Yeah, equal molecules and molecules and moles are the same. Yeah. So equal numbers of moles, I think do you just have 2 polymers in that example? Yeah. So what would the mole fraction be if you have equal number of moles or equal number of molecules? 0.5, right? Because the mole fraction has to add up to 1. Yeah. Any other questions? Yes.
Is this the same thing that we just did with the?
So now this is different. So we're calculating now distributions. We're not calculating we're not calculating M zeros. And so for this example, we've got one M0 copolymer, and we have 1 degree of polymerization, and we get 1 molecular weight. Or this example, it's a little bit easier to see, right? Right here, right? This gives you 1 molecular weight for 1 chain. Now, we're taking the next step that we have a mixture of chains, a mixture of lots of different chains, and these chains all have different XN, right? They all have different lengths, which means they all have different degrees of polymerization, and we're computing the average of the length of the chain, not the average of the monomer repeat units. Yeah, it'll take a little work to get that square. Yeah. This one? Yep.
Yeah, if we put the sum before X and non, would that be the same as the one that we just done? If we just put the sum, because then we would.
Well, that's not quite right, because X is not a mole fraction. In this, X is a degree of polymerization. It's not a mole fraction, so it's not the same. Yeah, if you want to use the summation notation, make sure you're summing around mole fraction, not degree of polymerization. Yeah, it's tricky. Nomenclature is not perfect. There's only so many letters, and so you just need to know from your context clues what means what. Yes.
So how exactly can we like convert from mole fraction to weight fraction?
I'll show you. That's what we're going to talk about next. All right, so you'll need that for your homework. Now on to MW, and MW is the hard one. It's the second moment, and it's the second moment because we square the mass of the chains. That's why it's called the second moment, and it's based on weight fraction. So the key is Mn is easy when you have the mole fraction. Mw is easy when you have the weight fraction. And then how do you get between mole fraction and weight fraction? We're going to talk about that in a second. And so Mw looks pretty easy because if you have the weight fractions, like in the homework, 1/3, 1/3, 1/3, all the same weights of a sample, you can calculate the weight fraction and calculate the MW. But there's no equation on the slide for Mn quite yet. I'll show you how that works in one more slide. So if we want to calculate the weight fraction, we can make a calculation like this. So we have 1 mole of 10,000 grams per mole. If we have 1 mole of 10,000 grams per mole stuff, how much does that weigh? 10,000 kilograms, or 10 kg. W equals. That's not weight fraction yet because we don't know the total mass. What's the weight if we have 2 moles of 12 kilogram per mole stuff? 24 kilograms. Remember, units count, and I'm multiplying kilograms per mole times moles, right? So that gives me the weight. And then, of course, the weight of this is 14 kilograms. So see what I did there? You're just multiplying to get the masses. If you've got moles and you know the molecular weight, you can get the mass, same as you've done since high school chemistry. And so now to get the weight fraction, you just take 10 kilograms and the total weight equals 10 plus 24 plus 14. That equals 48, I hope. And so you have the total weight, so you can calculate the weight fraction, which is just, it's easier if I point here. The weight of this divided by the total times its molecular weight. The weight of this times its total times its molecular weight. And I take that weighted average and I get MW right there. This, of course, is the same equation. We'll talk about it in a second. So you can use whichever equation makes sense to you. This one is super nice because you can step through it systematically. And so if you know the number of moles of each sample and you know the weight fraction of each sample, you're off to the races. You know the mole fraction, you know the weight fraction. That one is trickier because you have to wrap your heads around weight fractions, right? But you already did that in one of the other homework problems, converting between moles and weight fractions. That's just going to be really important. Make sure you keep your wits about you. And if you've read the book, there's some really useful ways to get MN if you have the weight fractions. And so remember, we're calculating MW in this one. That's easy. We have MW right here. And this is the key to unlock the last part of the homework, is you can calculate the MN or the M bar N, which is the number average molecular weight. If you do this summation, which is 1 over this summation term, so we already know what the weight fractions are. We know what the individual MNs are. They're both in the denominator, remember? So you have something that looks a little bit funny. So you've got M bar N equals 1 over weight of 1 over M of 1 plus weight of 2 for M of 2 plus weight of 3 for M3. Then you solve that for MN. Now, as you're going through this, notice approximately MW is kind of in the middle, right? It's kind of in the middle of the distribution. MN is in the middle of the distribution, but what's the key about MN and MW? MW is always going to be higher or the same value, right? And so since MN is the easy one, I got 12 kilograms per mole. Here I got 12.2. Those are totally reasonable. They're sort of in the middle. That's a reasonable answer. I can move on to the next question. So when you calculate MW and MN for whatever problem it was, is it 1.3? Make sure that your numbers sort of line up with this example. And the best way to do this is, you know, make a little drawing, make a little table, sort of use record keeping, just like I laid out in these slides. Write down your equation and then put a box around it or something. And make sure you say MW equals this. And you have a nice equation written out, nice one line. It's really easy to see how to grade that and make sure you know what you're doing. That's tricky. 1.3 is the hard question. Other questions on that? So what I don't want you to do is just try and plug and chug this, right? I don't want you to say, okay, this is really complicated, but I'm just going to start throwing stuff in there and make some crazy summation, you know, or I'm just going to, you know, write down this equation, plug it all into my calculator and hope that I get the right answer. I really want to see you lay it out just like this. I really want you to make a little diagram, some record keeping, show me the moles, show me the weights, make sure it's really clear. And then you're learning as you're doing the homework, rather than just trying to plug and chug it and say, well, the equation gave me the right answer. I'm not really sure how I got there, but you know, it seems to be fine. I'm just going to go with it. You know, so use the homework to help you learn. Did I see a hand?
No, it's okay.
Oh, okay. Okay. Any other questions? Yes.
Just a little bit confused about MN versus M bar N. Are they the same thing?
They're the same thing. Yeah. Yeah. When you see the bar, that indicates what mathematically? Do you remember? Average. Sometimes the bar will be there. Sometimes it's not there. It's not perfect nomenclature, but sometimes you'll see X. Sometimes you'll see X bar. You know, it's when you see the bar, we're definitely talking about the average. When you see it by yourself, you know, when you see X by itself, you know, like in this. Geez, if I can find it. Like in this, there is no average, right? We're only talking about one chain, but we still have the average repeat unit molecular weight because sometimes we need that. So, you know, it'll be clear when we get into it. Yeah. Other questions? All right. So as we start looking at this, so this is the formal slide on dispersity. I encourage you to look in the book as well, because it would have been really hard to solve the homework problem if you hadn't looked in the book and read the molecular weight section that's only like 3/4 of a page and found this, because this gives you MN from weight fractions. Right? So sometimes in the book, it gives you a shortcut and gives you a formula that you can use rather than having to do the accounting yourself. And so make sure you take a look at the book. Make sure you take a look at the book for dispersity as well. All right, pull out your clickers because I do want to take attendance. Clickers are C, D. All right, and this is a clicker question. Oh, hold on, I need to start the clickers. Nothing like taking attendance on a Friday. What's the dispersity? So this is a table. This tells you how many moles, tells you what their molecular weight is. It tells you what their mass is. I don't know why M is here. This should be W. I. So what's the dispersity of this sample? What is dispersity in the first place? MW over MN. So what in this table tells you what MW is, and what in this table tells you what MN is? Can it be A? No, it's less than 1, can never be less than 1. Can't be C either. So you've narrowed it down to 3 choices. D looks a little dicey. That's a really high dispersity, but it could be that. And so right away, you get it within the ballpark. Okay, we need at least 40. Keep going. 45 would be awesome. 50 would be great because I think that's how many people should be here. All right, that's looking good. Make sure to get in your answers because again, this is the participation. So we look at this table and we've got MI and then we have the mass times the moles, and it turns out that we can get all of our quantities from this table, so we can calculate the MW from this. And so when you go back and look at this, make sure you figure that out. We can get the MN from this as well. And so finally, if we have an MW of 15,362 and an MN of 14,980, our dispersity is going to be 1.03. So we don't have quite as much time as I wanted to have for that, but make sure you look at this example and follow it down. What each of these quantities are, what's MN, what's MW. You're going to have to do this on homework number 2 when we talk a lot about distributions, and this is a way to do the accounting. All right, ask questions on homework after class if you need to. I'll be around this afternoon, but not too late. You can ask a question after class. Yeah.
Why would we use regular
For MN here, yeah, I mean, you could plug the distribution in right here if you wanted to. You could use the NI times M's and you're all set. Yeah. Okay. Let me stop.